In my lab, I observed the motion of a volleyball moving across a flat surface. My objective is to understand and predict the motion of this volleyball. I can use Newton's second law to model the ball's movement, and I found that my model predictions are very similar to the experimental results. Here's a video of my volleyball moving across the flat surface. So now I'm going to go through the Newton's second law, the equation we use to calculate the constant velocity of the ball's movement. So Newton's second law states that the final velocity equals the initial velocity plus the net forces acting on the object divided by the mass of the object times the change in time. So for our example, there are no net forces acting on the object, as you can see in the video, because in the video there are no external forces that can be seen acting on the object, so we just assume that F net is 0. So because this F net is 0, then this whole side of the equation is 0, which makes the final velocity equal the initial velocity. So because the initial velocity equals the final velocity, the ball should be moving at a constant velocity throughout the experiment. The method I use to find this constant velocity is that I use this equation here, velocity equals the change in position over the change in time, and I chose two experimental points and calculated the change in that position over the change in its respective time, and I plugged in this velocity into my VPython program. And the way that the program plots the position versus time graph is that it uses this equation down here. The final position equals the initial position plus this constant velocity that I calculated up here times the change in time. So now we can go back to my experimental data, and I will show you how I chose the points to calculate the velocity. So in reality, you could choose any 2 points and find the difference in position over the different time. So you could go from this first to the second point, from the or from the first to all the way to the last point over here. So after I calculated the velocity, I then plugged that into my VPython program and ran the module. And as you can see, the ball moves very similarly, or the ball moves the same as in the video, and the line is very similar also. I used Google Sheets to compare my experimental and actual results. So here on the left is when I used the velocity between this second and third points. So this second and third point here has the same slope as my whole model position line. I realized that this method was flawed and it was not very accurate. So instead, I used the initial position, the first position point, and the last one over here, and found the change in position over the change in time, and used that as my velocity, and it was a much more accurate velocity than the first one. And if we were to flip the axes so that the time was on the y-axis and the position was on the x-axis, none of the calculations regarding with the change in position over change in time to find the velocity would change at all. It would just flip the time and position, and the physics equations do not change, so therefore the results also would not be changed. I would also like to state that it is impossible to say how many pushes and pulls are added together to give a zero net force in the case that we observe, because there are many different forces that can be acting on the object, like friction or air resistance, but there is no way to tell the quantity or if the force is apparent in the case of the volleyball that I observed. We can only look at the data, which shows that there is a constant velocity because of the linear line, which means there is a zero net force. And these have been my observations from Lab 1. Thank you for your time.